An interesting thing happens with silicon now. If we understand diffusion and drift current, and we take two pieces of silicon, we can't just glue them together. We take a p-type and an n-type, and the junction is still covalently bonded. It's still lattice. It still has to have the perfect structure from one side to the other. And we're just going to define some things, and this may look familiar from before. Anode and cathode. And we have an N-type piece and a P-type piece, and they're directly in contact. And when it first starts out, if we were to observe the moment when these are brought together, we'd have evenly distributed charge. And it's as if this P-type isn't here. The N-type is oblivious. All those electrons are oblivious that there's P-type over here. Same, if we do this, the holes are oblivious. But obviously what happens when this occurs is this, they're attracted to each other. The hole and the electrons say, you know what, that looks pretty good to me, and they start annihilating each other. Okay? They fall in love, and we end up with over here bound electrons and bound holes. And though it seems funny that the holes move and not the electrons, but this is what exactly happens. And we end up with, from one side to the other, we end up with the recombination. And maybe it stops at a certain level, and I've just drawn it right here. I'm going to label this W for the depletion width. So this is the depletion width. And we got to a certain point where these electrons don't feel like crossing this boundary to the holes, and the holes likewise don't feel like moving across that barrier. And if we were to plot this, and we were to say this is X, given that this is lined up perfectly with that, and then we have a 0 voltage thing that goes down here, and what we end up with is potential. And this makes sense. It kind of looks like the anode-cathode battery type configuration. We end up with charge bound, and we have a difference in voltage from one. It looks like we end up with an E field. If we end up with an E field, okay, and they actually draw it the opposite way, so I got it wrong. We end up with an E field from here to here that's just naturally built in there. Now, you aren't going to be able to measure this, but we do see this as the junction voltage. Let me draw out the equation for that. The junction voltage is equal to VT natural log NA ND over NI squared. And just so that we don't get lost in the equations, let's bring that forward. Let's find that equation. First of all, thermal voltage, KT over Q. Junction voltage, V0 is equal to VT, natural log, NA, the acceptor concentration on the P-type, the donor concentration on the N-type, and an NI squared. So NI comes up a lot. And so this is an important relationship. It gives us that value. And guess what V0 is going to turn out to be? Someplace between 0.6 and 0.9 volts. So let me move this back. So this turns out to be 0.6 to 0.9 volts. That resides someplace close to, and these are positive values, but that resides someplace close to where 0.7 volts is. And so that's where we get it. Notice there's a natural log. There's all sorts of interesting things that exist with this. And we're just going to have to take it at faith for right now. Now, we're going to have to start at scratch here. And let's just say for a second that there's my junction. Let's just say that I unevenly distribute. In other words, I have way more holes than I do electrons. Okay, so lots. And over here I have an occasional electron. Well, as it turns out, we can make the individual gaps from this because this is before it's bound. And what's going to end up happening is we're going to have, I'm going to call this negative xp. So we're going to call this 0. This is negative xp. This is xn. Okay? We're going to have xn much greater than xp. Okay? And so that's kind of expected that we'd get this, and we'd end up with negative bound charges over here. But they'd quickly build up a barrier over there, much more than these positive charges over here. But the positive charges are going to build up a wider area. And so we have some equations to design to find that as well. But this shifts the energy levels. Okay, this shifts it to where our voltage. So once again, if we were to plot this, now that the center of that, so this is our actual junction, but the center of it is going to be someplace over here to the right. Okay, we're still going to end up with the same kind of equation for the junction voltage. And so that's all kind of actually interesting. And we can play this one way versus the other. And this is how we play with semiconductor physics. There's lots of different things. So let's just pause for a second and think about the things that we can be in control of for a second. First of all, the cross-sectional area. Cross-sectional area is going to determine how big of a junction we have. What else do we have? We can control NA. We can control ND. And we just saw how that's going to affect the junction. And we can control the ratio of these. And so far, we have 3 dimensions that we can control with this. There's also temperature out there, and I'm just going to put that out here. Generally, that's something that just happens rather than something that we design for. And let me see. There aren't a lot of other things that we can change about this junction other than those 3 things. That's what we're going to use if we were actually building a diode ourselves. What we would do is we would make a junction, and we'd have to base on this. Now, an advanced electronics course is going to teach you how to make special junctions. But this should help us kind of understand, these 3 things should help us understand how we're going to change how the next few equations. So the first one is that depletion width on the N side versus the depletion side on the P side is equal to NA over ND. So acceptor, this is the holes, this is electrons, and so they're inversely proportional. The more holes we have, the wider the depletion region is going to be, or the ratio is going to be on the N side. Okay, and so these are inversely proportional. The other equation that we can do is we can say the width is equal, and this is kind of a dope equation, xp plus xn, which is equal to, here comes a big long exponential, 2 epsilon s, which we'll have to define, over q, 1 over NA plus 1 over ND. And then we're going to put the junction voltage out there. Okay, I've got this in document format, so you don't have to read my scrawl. So that's coming up here in just a second. And let's see. So epsilon s is the permittivity of silicon, which is equal to 11.7 times epsilon naught. Epsilon naught is the permittivity of free space, which is equal to 8.85 times 10 to the negative 14th. farads per centimeter. And both of these combined together gives us an epsilon s that's equal to something like 1.04 times 10 to the negative 12 farads per centimeters. Notice that we're doing this in units of farads per centimeter. So these are all in the book, but these are the general equations. I think this is probably going to be the most important one. And this doesn't change for silicon. If we were to do germanium, it would have a different value. But we're doing, for this class, we're only thinking about silicon. So that's nice. We can also extrapolate out xn from, if we know the width, is equal to NA over NA plus ND. We can also extrapolate out XP, times ND over NA plus ND. And let's just pause for station identification. What I'm going to do is I'm going to bring up my equation sheet. So that's the first one, xn over xp is equal to NA over ND. Depletion width calculation is right there. And the ones I just wrote down are right there as well. And the next one is junction charge. Well, before I get into junction charge too much, let me bring up video capture again. Let's go back and take a look at this dude. Remember, all those bound charges leave a depletion region, but we still have all these holes over here. And all these electrons. Remember, this is our depletion region. Okay? And what this kind of looks like, look, we've got basically a dielectric. What happened is in this region, when we have that recombination, we have excess electrons, excess holes, and they recombine. We end up with a dielectric between these. In other words, the holes and the electrons don't like to travel across it very easily. Well, what that means for us is we have charge on one side versus charge on the other. And what else looks like this? Minus over here. It has capacitance. There's charge built up on two parallel plates. And so we want to be able to quantify how much capacitance is there. For good or for bad, it's there. And the other thing is, if we reverse bias this, the width is going to get wider. Okay, it's going to push the holes this way. We're going to shove in electrons here, which is going to pull this side back. We're going to shove in holes. We're going to really remove electrons, which is going to pull in holes from this side, and it's going to make the width wider. And so we're going to end up with a different capacitance. Okay, well, we don't start with capacitance. We start with charge. And this is that equation that I just had up there. I guess that's a capital J, is equal to cross-sectional area. Once again, what are the things that we have control? NA and D. Those are the three things that we can control. So we can come up with a junction capacity or junction charge of 2 epsilon s times Q NA times ND over NA plus ND times V0. That is our junction charge. Okay, that's how much charge will be there if we aren't messing with the junction, if we aren't trying to push electrons through one way or the other. And so I suppose we can do an equation for this as far as finding out exactly how much charge is there. I don't think I would really like to. But it does, this particular example does give us a lot of stuff to go on. So let's make the long example, and then we'll do a separate voltage for when we start applying voltage. A separate lecture for that. And so they said we have a p-n junction. It's in equilibrium. We have T is equal to 300K. We have NA on one side is equal to 10 to the 18th per centimeter cubed. Or sorry, yeah, per centimeter cubed. We have an ND side that's equal to 10 to the 16th per centimeter cubed. We have cross-sectional area is equal to, and they were nice to us, 10 to the minus 4 centimeters squared. They could have very well given this in cubic, in square microns, in square anything. So they were nice to us. And they want us to calculate whole bunches of stuff. P sub P, N sub P0, P sub, or N sub N, P sub N0. They want us to know the junction voltage, the width, XP, XN, and they want us to use Ni is equal to 1.5 times 10 to the 10th. I'm going to switch over, I think, completely to MATLAB at this point because it just turns into math, okay? And so don't freak out that I'm going over to MATLAB. But here we go. All right, so let's bring out our Q. We're going to need that. Let's put in all the other values that they gave us. T is equal to 300. Okay. K is equal to, I want the other one. There. Capital K is how I define that one. NA is equal to 10 to the 18th. And D is equal to 10 to the 16th. A is equal to 10 e to the minus 4, or 10, no, it's 10 to the minus 4. There's a difference, okay? Obviously, it's a factor of 10 difference. It's an order of magnitude. The first thing that they want us to do is calculate P sub P. P sub P, I'm just going to say PP for this, is equal to approximately NA, okay? That's acceptors or holes. This is the P side because the P, so that's it. Okay, so that was really easy. N sub P, okay, is equal to, if we go back to mass action law, okay, and it's going to be Ni to the second divided by P sub P. Okay. And I didn't find Ni. Okay, 225. And that's what it has here in the book as well. So we did that one right. N sub N is equal to our ND. And P sub N is equal to mass action law to the second divided by NN. And that's 22,500, which is the same result that we'd expect for this. And those are so small, we never use those values. So that's the PN0, NP0 and a PN0 that they're talking about in the book. Okay. They did want us to come up with a junction voltage VT. KT over Q, K times T over Q. And I did mean that one, 25.9 millivolts is what we get. And now they want us to calculate V0. Now V0, if we go back and we look at the equation that's in the equation sheet, and let's move this dude up. Okay. And we're going to find where that was. There it is. VT times natural log VT times log, in MATLAB log is the natural log of NA times ND divided by NI to the second. 0.813 volts. Okay, that's what the junction is. Does that seem reasonable? Yeah, that seems reasonable. Okay, and now they want us to do the depletion width. So there's a great utility in the back of this chapter. Okay, and so in that utility just has there's just a list of all these equations. Use it. W is equal to square root of, so let's define epsilon. Epsilon SI is equal to 11.7 times U. And this is where I forget what that value is, 8.85 e to the minus 14th. Okay? And so now we go back and we run that equation. This is why MATLAB is so nice, by the way. W is equal to square root of 2 times epsilon over Q times 1 over NA plus 1 over ND, do trust order of operations, times V0. And this gives us that the width is 1 micron, about 1 micron width. Does that sound right? Well, the book disagrees with me, and so I have something wrong in my equation. 2 epsilon, and I don't see a particular issue with what I've got. Let me see. V0 is the only thing. Yeah, that one looks good. And so let's try this again. Did I forget a factor of 2? Nope. Divide by Q times 1 over NA plus 1 over ND times 0.814. Let's look at psi. 1.04. I've got a factor different with my epsilon. There's some difference here. Times 10 to the negative 12th. And so I put in something wrong for this. Let's go back to the books. 11.7 times 8.85 times 10 to the negative 14. So that would make a difference. So now I've got really what they've got now, which is really good. 0.325 microns. Okay, or 327. They want to know xn is equal to W times NA over NA plus ND. And that gives us the majority of it is xn. XP is equal to W times ND divided by NA plus ND. Remember the orders of magnitude on these. Okay, there's 2 orders of magnitude between them, and that's 2 orders of magnitude smaller, so that makes sense. Okay, so those are extremely small. The XP is extremely small compared to the other one. And finally, the junction charge, which I have written right there and ready to go. QJ is equal to A times, is A in the right units? Yes, it is. Square root of 2 times epsilon, epsi times Q times NA times ND divided by NA plus ND times V0. And that gives us that this is how many coulombs are stored on there, 5.165 times 10 to the negative 12. So 5.165 picocoulombs is what's going to be stored on there. Okay, we've solved it for everything that they wanted to. It gives you an idea of how you manipulate these numbers. Of course, with a calculator, you're going to have all sorts of issues, keeping track. So that is junction charge.